Hello everyone, I welcome you all for third lecture on partial differential equations. In this lecture, I will discuss about the particular solution of Lagrange partial differential equations, how to find out that, and numerical problems. The Lagrange partial differential equation is given by 1, and corresponding to this partial differential equation, the auxiliary equations are dx upon p equal to dy upon q equal to dz upon r. The general solution of this Lagrange partial differential equation is written as capital F u comma v equal to 0, where f is an arbitrary function. U and v, they are functions of x, y, z, and we obtain these solutions u and v by solving the auxiliary equations. While writing the auxiliary function f, we don't know what is the exact relation between u and v, or we can say c1 and c2. If using some information, we can find out some relation between these constants c1 and c2, then we substitute the value of c1 and c2 in terms of u and v, and then we can find out the particular solution of the Lagrange partial differential equation, which is given by 1. So the particular solution of the Lagrange partial differential equation is obtained as using some given information like find the integral surface or a particular solution of the partial differential equation passing through given surfaces. So some condition is given to us, maybe plane or some curve. Then we try to find out a relation between C1 and C2 using these given conditions. For example, we have some relation between C1 and C2 as C1 plus C2 equal to 1. Then we substitute the values of C1 and C2 in terms of u and v, and we obtain a particular solution of the partial differential equation 1. Consider example 1. We have to find out a particular solution of partial differential equation 1 passing through the straight line x plus y equal to 0 and z equal to 1 given by 2. In 2, we have two equations, x plus y equal to 0, which is a plane, and z equal to 1 is also a plane. And intersection of two planes is a straight line. So we have to find out a particular solution of partial differential equation 1 passing through this straight line, which is the intersection of two planes given by 2. So we start with the auxiliary equations corresponding to partial differential equation 1, that I am writing as 3 dx upon x into y square plus z equal to dy divided by minus y into x square plus z. This is equal to dz upon x square minus y square into z. If we see these auxiliary equations carefully, in the denominator x, y and z all are mixed. So we don't have a clear-cut combination here. So we have to look for the combinations. See the first two ratios with the dx and dy. In the denominator, we have xz in the first ratio, and with the dy we have minus yz, and with the dz we have z times x square minus y square. So we can have some idea that we use the first two terms dx and dy and try to eliminate z from these two ratios. So the first combination is multiply first ratio with x and second ratio with y, add them, and now you can compare that with the third term dz. We have this combination x dx plus y dy minus z dz. I have written as minus dz. You can compare these two ratios also, that x dx plus y dy, this is equal to dz also, and in this case the denominator of this ratio or this combination is 0. So it implies that numerator part is also 0. So the first one is x dx plus y dy minus z dz equal to 0. Integrate that. We have the first integral curve given by equation number 4, x square plus y square minus 2z equal to c1. Now we can have one more combination, y times first ratio plus x times second. In the first combination we try to cancel that z part. Now we are trying to eliminate x and y terms, and let's see what will happen. So we can have y times first plus x times second. Then I will compare this with the third ratio, that is dz. So we have this type of combination, y dx plus x dy. If we simplify the denominator of this combination, it comes out to be xy I can take common, and finally with differential of xy we have in the denominator minus xy into x square minus y square, and now I can combine this or compare this with the third ratio, that is dz upon z times x square minus y square. Cancel this term x square minus y square. Now we can integrate this easily, and the final second integral curve is x y z equal to c2 given by equation number 5. So we can write down the general solution also by the last relation, that capital F, which is function of x square plus y square minus 2z comma xyz equal to 0. Now the next part, how to find out the particular solution of this problem. So write down the condition given to us, x plus y equal to 0, z equal to 1. This is the same as the second equation on the previous slide. Now we will use given two surfaces integral curves, that is u function, v function given by equation number 4 and 5 respectively, and the given condition through which the surface is passing, that is equation number 6. Now we have three equations in terms of x, y and z, and two constant c1 and c2. Now using these three equations we try to find out some relation between c1 and c2. Once we have that relation, we just put the value of c1 and c2 in terms of x, y and z, and we get the particular solution. Now how to do that thing? Start with the given condition through which the surface is passing. For example, in this we have equation number 6. Write down the parametric equation of this surface or the condition. So here z is always a 1, so z is 1. X plus y is 0. It means if x is t, then y will be minus t. So I'm writing equation number 6 or condition given by 6 in terms of parametric equations, and they are given by x equal to t, y equal to minus t, z equal to 1. See the box on the slide. Now use this parametric form in equation number 4 and 5, two integral curves which we got from the auxiliary equations. Now we have equation number 4, put the value of x as t, y as minus t, z equal to 1. We get equation number 7. And from equation number 5, we again put the value of x, y, z in terms of t and constant. We get equation number 8. Now see equation number 7 and 8. We have c1, c2 and this parameter t. So try to eliminate t from these two equations. If we are able to do that, we have some relation in c1 and c2. So c7 and 8. From equation number 8, I can find out what is t square. So put that value in equation number 7, and finally I have this relation c1 plus 2c2 plus 2 equal to 0. Now put the value of C1 and C2. We have the final solution of the partial differential equation. Consider example number 2, the partial differential equation given by 1. We have to find out its particular solution which passes through this circle given by 2, z equal to 0, which is a plane, and x square plus y square equal to 2x, this is a cylinder, and the intersection of this cylinder and this plane z equal to 0 is a circle. So we write down the auxiliary equations corresponding to partial differential equation 1, which I am writing as 3 dx upon 2 times yz minus 3 equal to dy divided by 2x minus z equal to dz upon y times 2x minus 3. I am denoting these three ratios as 1, 2 and 3. Now we have to look for the combinations. Try to find out a combination in which we have just two variables. So see the first and the third term, dx and dz. In the denominator part, y is appearing, so we can cancel y and we just have x and z, and we can easily integrate that. And now we have finally dx upon 2 times z minus 3. This is equal to dz divided by 2x minus 3. This is first order partial differential equation, variable separable form, so you can easily integrate this. And we have the first integral curve given by equation number 4, which is x square minus 3x minus z square plus 6z equal to c1. Now we have to look for the second combination. In the second combination, we have multiplied the first ratio by x and multiply the third ratio by z and then compare it with the second one. Till now we have not used the second ratio, so we have to use that. And if you see the denominator part of that ratio, we have 2x minus z. So what we have to do, we will use first and the third ratio and we will try to make a combination so that we can have 2x minus z with that new combination. So try this combination, x times first ratio minus z times third ratio. Then on the left hand side of the next equation, we have x dx minus z dz divided by minus 3y into 2x minus z. And now we can easily compare this with the second ratio, dy upon 2x minus z, which is given by equation number 5. Now cancel this 2x minus z and now we can simplify this. I am rewriting equation number 5. Cancel the common term on both sides. Simplify this, and finally we have the second integral curve given by equation number 6. So we have the general solution given by the last expression on this slide, where this capital F is an arbitrary function. You can avoid this step of writing the general solution as we have to find out the particular solution only. Now for finding the particular solution, I am rewriting the conditions. That is the circle through which we have to pass the given surface. So it is z equal to 0 and the cylinder is x square plus y square equal to 2x. Now we have to write down the parametric equation. Z is always 0, so keep it as it is. Now out of x and y, it is quadratic equation in x and y. So we have to see this carefully. In the two surfaces, integral curves which we got from the auxiliary equations in terms of C1 and C2, there is no term with y as simple y. We have y as y squared in those expressions. We don't need y. So here in this parametric form, I am taking x as t. Then using the cylinder equation, we have y square is given by 2t minus t square. See the equation 7 or relation 7 in the box. So this is the final parametric form. Now we use this 7 in equation number 4 and 6, the integral surfaces or the curves. Then equation 4 reduces to, use this relation 7 here. It is t square minus 3t equal to c1 given by equation number 8. And the second integral curve 6, it reduces to t square plus 3 times 2t minus t square. This is equal to c2. Simplify this, we have equation number 9. Now from equation number 8 and equation number 9, try to eliminate t so that we can have some relation in c1 and c2. Now for this we multiply equation number 8 by 2 and add it to equation number 9, and finally we have a relation in c1 and c2, which is given by equation number 10. 2 times c1 plus c2, this is equal to 0. Now put the value of c1 and c2 from equation number 4 and equation number 6, and we have the final particular solution of the partial differential equation 1. Consider the partial differential equation given by 1. We have to find out its general solution and then its particular solution, which passes through the line given by x equal to 1, y equal to 0 given by 2. X equal to 1 and y equal to 0. These are two planes, and intersection of these two planes is a line. So write down the auxiliary equation corresponding to the partial differential equation 1. The auxiliary equation is given by 3. Mark these three ratios as 1, 2 and 3. See the auxiliary equations given by 3. In the denominator x, y and z, all three variables are mixed. We don't have a clear-cut combination with the two variables only. So we have to look for the denominator and we'll try to make some suitable combination. See the first term dx. Here we have in denominator 2xy, and with the third term dz, we have minus 2yz. So if we multiply first ratio by z, then in denominator we will have 2xy, and we multiply third ratio by x, then in denominator we have minus 2xyz, and if we add these two, this part will cancel out. So let's try this combination. First ratio multiply by z and add it to x times third ratio. So finally we have z dx plus x dz. You can simplify the denominator. Denominator will be minus z minus 2x square. Now see the second ratio with the dy. We have the same denominator, so now we can combine this combination with the second ratio, that is dy. Denominator will cancel out. Simplify the numerator part, and finally we have the first integral curve xz plus y equal to c1 given by 4. Now for the second combination, we have to again look for the ratios. Consider first and second ratio. With dx in the denominator we have 2xy, and with dy we have minus 2x square. So if we multiply dx ratio with x and dy with y, and we add these two, then this part will cancel out. So let's try this combination. X times first ratio plus y times second ratio, then we have x dx plus y dy. Simplify the denominator, cancel the same terms with negative signs, and finally we have x dx plus y dy divided by minus x plus y times z. Now we can compare this with the third ratio because the denominator is same. So it is 2 times x minus yz with dz ratio, right? Now cancel this x minus yz because it is same on both sides. Now simplify this expression, integrate it. We have the second integral curve given by 5, which is x square plus y square plus z equal to c2. The general solution we can easily write down using any arbitrary function f. Let's discuss how to find out the particular solution. Here the given conditions are x equal to 1, y equal to 0. There is no restriction on z, so we can take z as the parameter t. Now use this parametric form and substitute this in equation number 4 and 5. Equation 4 reduces to t equal to c1 and equation number 5 reduces to 1 plus t equal to c2. Now from these two equations in the boxes, you can easily eliminate c1 and c2. And finally, the relation between c1 and c2 is 1 plus c1 equal to c2. Now substitute the value of c1 and c2. Finally, we have the particular solution given in the box. Now consider this example number 4. We have to find out the general solution of the partial differential equation given by 1, and then we have to deduce that equation number 2, which is yz into z square plus yz minus 2y equal to x square, is a solution of this partial differential equation 1. Here we don't have any condition, we have the particular solution. So we have to guess that what should be the suitable relationship between c1 and c2 so that we can have equation number 2 as a particular solution of this partial differential equation 1. So let's start with the auxiliary equations given by 3. Mark these ratios as a 1, 2 and 3. Now try to look for the combination here. See the second and the third ratio. We have only two variables, y and z. So we can solve these two. Start with second and third. Now this is a first order ordinary differential equation. You can solve it again by any of the techniques, checking the exactness, Leibniz. Here I am writing this equation in terms of Bernoulli's equation, given by the third equation on this slide. I'm using this substitution that minus 1 upon y I'm putting equal to t, and finally I can rewrite this differential equation as differential equation number 4, which is simple Leibniz linear differential equation, and I can easily find out its solution. Here the integrating factor is e raised to power 1 by z dz, which is on simplification as z. So the solution of this first order partial differential equation, that is Bernoulli's equation, you can simplify this. See the calculation part carefully. And finally I have the answer given by equation number 5, 2y minus z square divided by yz equal to c1. So this is the first integral curve corresponding to those auxiliary equations. As discussed in lecture 2, if you are not able to find out any combination, then try to look for few combinations like dx plus dy plus dz or x dx plus y dy plus z dz. If you see here the auxiliary equations, there is one thing common. With dx, we have x common in denominator, with dy we have y, and with dz we have z. So try to look for this combination dx upon x plus dy upon y plus dz upon z, or some other combination. Here if we see the denominator terms carefully, the combination which we can apply is dx upon x minus dy upon y minus dz upon z, and in this case the denominator part is becoming 0. So the numerator is also going to be 0. So finally we have the second combination as dx upon x minus dy upon y minus dz upon z, and we can easily integrate this one, and finally the answer is x upon yz equal to c2 given by equation number 6. So finally we have two integral curves given by 5 and 6. Now using 5 and 6 we have to show that the function given in box yz times z square plus yz minus 2y, this is equal to x square. This is a particular solution of the partial differential equation 1. Now we try to rewrite this particular solution in terms of relation 5 and 6, or you can directly guess what should be the suitable relation between C1 and C2 so that we can have this solution given in box. So here I am trying to rewrite the particular solution in terms of equation number 5 and equation number 6. You can try a different approach also, but this is one of the approaches here. See, in the C1 we have 2y minus z square divided by yz, right? So in this particular solution, the bracket expression z square plus yz minus 2y, I am rewriting this one as bracket term only yz minus 2y minus z square. And see this bracket part, smaller one, 2y minus z square, it is the numerator of the function in C1. We just need yz. So on the left hand side I am taking yz common. Then we have yz square into 1 minus 2y minus z square divided by yz. This is equal to x square. And now this expression on the right hand side, x square, I can divide by this x square, right? Now see the second expression on this slide. I have underlined. The first expression in the bracket is equation number 6, and this is 1 by C2, right? Its whole square. And in the second bracket we have fifth equation, same expression. So if C1 and C2, they are related by relation given by 7, 1 upon C2 whole square into 1 minus C1, this is equal to 1. So this is the required relation between C1 and C2. Try these 3 numerical problems. You can find out the general solution first and then try to find out the particular solution of these partial differential equations passing through the given curves. As such, there is no hard and fast rule about the combinations. You have to practice for that. But try to look for the terms and try to see how can we simplify that so that we can get some suitable combination and we can simplify the problems.